Hello everyone, welcome back to another lesson. In this lesson, we will be talking about the Kirchhoff laws. So Mr. Kirchhoff was a German physicist, and he was able to establish the relationship between partial current and the total current that comes out of a power source, as well as partial voltages relative to the total voltage that comes out of a power source. So let's take a look at current intensity first. So on the left-hand side, we have a series circuit. We recognize it because there is only one pathway. And on the right-hand side, we have a parallel circuit. And we know this because there are several pathways. So let's take a look at the series circuit first. So if you remember, current basically is the amount of electrons that circulate in a circuit. So it's the amount of charges that move around a circuit. So my electrons are looping around like this. So whether I count the amount of electrons that pass through this point, or through this point, or through this point, or through this point using these various ammeters, I should always get the same measurement because there's only one pathway. So I'm always going to be counting the same electrons. They can't go anywhere else. So that's why the law says that I total means the current that comes from the power source. So I total is equal to I1, so my first ammeter, I2, same reading at I2. It should be the same reading at I3 and the same reading at I4. So all their values are equal. Okay, so that's how it works. So if, for example, my power source was giving me 20 amps, well then this reading should be 20 amps. This reading should be 20 amps. This one as well. And this one as well. It only makes sense. Now, don't forget, I mentioned this in the past, sometimes because the current is very weak, we're going to be measuring in milliamps rather than in amps. So that means in 1 amp, I have 1,000 milliamps. Or I could say that 1 milliamp is equal to 0.001, so a thousandth of an amp. Okay, so it's important to remember this. Always verify when you solve, when you're working with the circuit. If you see something in milliamps, that should be the first thing that you do. Convert your milliamps back into amps because these calculations only work with amps, not milliamps. Okay? Okay, for a parallel circuit, so let's say that my power source has an output of 20 amps as well. Well, my electrons are all going through this ammeter, so they will all get counted over here because they haven't reached a node yet. So that means this one would be 20. But then at this point, they split up, right? So let's say they split 10 go here, and the other 10 go down here, but then they split again at this point, at this node. So let's say I had 2 amps that goes here, so that means I should have 8 that go here because they have nowhere else to go. It's not as if they can fly out of the circuit and just disappear. So I have 10 plus 2 plus 8 give me my 20. And that's what the law says. I total is equal to I1 plus I2 plus I3 plus, depending on how many branches you have in your parallel section. So your currents should add up to the total amount of current that is provided by the power source. Now, obviously this here is a little bit separate from my calculation just because here all current must go through this ammeter. So this law for the parallel law for current applies only to the parallel section of my circuit. That should be obvious. Now, since my currents, my little partial currents, merge together here and here at these nodes. Now the total current is circulating here back to the power source. So this ammeter should pick up a reading that is equivalent to the total current as well. So again, don't get confused. This law, which is for a parallel circuit or a parallel part of the circuit, this only applies to this section of my circuit, which is the parallel part of the circuit. Okay, so in series, the current is the same everywhere. In parallel, the currents, the partial currents add up to give you the total current that was created or that was given out by the power source. Okay, so that's the Kirchhoff law or laws, I should say, for current intensity. Now let's take a look at voltage or power or potential difference. So for the potential difference, it's a little bit different. Now, potential difference, it's more or less the amount of energy that the electrons will give up at any given point of the circuit. So let's say, just to use a similar number, let's say my power source gives out 20 volts of quote-unquote energy. Now you have to know that my electrons, when they leave, they have that 20 volts. When they come back, they have to have 0. They have to spend it all, okay? So they leave over here with 20, they come back over here with 0. And that's why we call it potential difference. If they leave over here with 20 and they come back with 0, well, difference means one minus the other, right? So 20 minus 0 gives me 20. Right? So how much did they spend overall by going all around? They spent 20. Okay, so that's why we call it potential difference, and that's why the voltmeter is always connected in a parallel way. We say across a certain component. Okay, so my electrons leave, and they have 20 volts, and they decide that they spend, not they decide, but it just happens that way, they spend 10 volts over here. And then they continue their journey, and let's say they spend 2 volts over here, and here they're going to spend 8, because as I just said, they have to spend everything before they come back. That's the way it works. So if you look carefully, we have 10 and 2 and 8. These numbers add up to the original 20 volts that they left with. So that's why the law says V total in series is equal to V1 plus V2 plus V3. The values of the various voltages will add up to the total voltage that was given out by the power source. Okay, so we said before in series the current is the same everywhere, but now we know that the voltages add up. Now, if we make a comparison with the parallel circuit, so let's pretend that my electrons have 20 volts as well. They leave with 20 volts. So my power source has an output of 20 volts. So my electrons will leave. And now at this point, they will decide, they will split up, and some of them will go through here. So let's say some of them go through here. Now, what will they do? They'll go through this branch and come back. But we know that they have to spend all of their voltage. Well, if they only go through this resistor, automatically they have to spend their 20 volts over here, since they have to spend it all before they go back. Now let's say I have another batch of these electrons that come down here and go through this resistor instead and then go back. Well, since they're only going to go through this resistor, they are forced to spend all 20 volts, since they're only going through one component before going back to the power source. But what if instead some of them decide they want to go through the light bulb? Well, they're only going to be going through the light bulb before they go back. Because if you remember, these circuits are always unidirectional, so they only go one way, right? So it's not as if they can loop around and la 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 and go back and forth. No. That's not the way it works. So they will go through the light bulb and go back to the power source. Well, if they're only going through this light bulb and that's it, they have to spend all 20 volts over here. Well, look at that. 20, 20, 20, 20. So the law says, in parallel, the total voltage is equal to the voltage that the electrons will spend in the first branch of the parallel circuit, which is also the same as the second branch of the parallel circuit, and the third branch of the parallel circuit, and the fourth and the fifth and the sixth if there are more branches to your system, to your circuit. Okay, so the voltage is the same everywhere. But if you recall for the current, in parallel, the current splits up, right? Because my electrons can go here, or here, or here. So it's basically opposite. Now, let me show you visually all equations in a chart. Maybe that will help you understand what I'm talking about. So this is what it would look like if we put all the equations together. So we saw in a previous, lesson, we saw the law for equivalent resistance. So equivalent resistance, we add them up in series and we do 1 over R in parallel, but that's not what I'm interested in. In series, the current is the same everywhere because it's the same electrons circulating throughout the one pathway, but they have to spend their voltage in various components before they go back to the power source. So these voltages add up. Now, if we look at the parallel laws, well, the various currents or partial currents add up because the current splits up between the different branches of the parallel circuit. But because they're only going through one branch, they have to spend all of their voltage in that specific branch. So that means that all branches will have the same voltage. So you can see that current is all the same in in series. Current is all the same in series, but voltage is all the same in parallel. And that will come in handy in the next lesson when we start solving for various values within a circuit. All right, so that's all I wanted to talk about in this lesson. So if you have questions, you know what to do. Otherwise, I'll see you around for your next lesson. And until then, take care.